Good afternoon, everybody. So the last lecture, we were discussing about determination of this magnetic structure using magnetic symmetries. And
That's the question which I emailed to you.
yes. So there's a question which was asked that if your magnetic intensity cannot be generated by all the representation which you get from the symmetry analysis, in principle, it should not happen. But it might happen then either you have not determined your crystal structure correctly, or there may be some phase transition nearby the magnetic phase transition. But suppose if you have this situation and you are not getting proper magnetic intensity by taking this symmetric consideration into the account, then what you can do is you can make this simulated annealing file, which I am going to show it to you today, that by making this simulated annealing file, how we can get still the information about the magnetic structure. So this is the case. So when I will run this simulated annealing part, then I will try to remove all the restriction from the symmetry side. So let me start this same example. So what we do in that case is, so this is today's date, and let's try to run this file in the, I go to, so this is paramagnetic phase of this sample, Li Ni 0.5, Mn 1.504. Let me just quickly have a look at the file again. So this is only nuclear phase. So how we proceed in those cases that we start with the paramagnetic phase, and then you first try to complete this refinement of the nuclear phase. So let me quickly run it. Let me see from where it has run. So this is paramagnet. It has not asked me any data file. So in this folder, let's see if we have data file. So data file also exists. So it has run this program, and now what we see is the only crystal structure part, and you can see it in better way what it has done. So here, when you see the marker, so it is only showing one marker corresponding to only phase number 1. It means it is the nuclear phase only. And this is the same sample on which we were working. And now the idea is, suppose you do not want to go ahead with this symmetry analysis, or you want to remove the restriction associated with the magnetic structure which comes from the symmetry analysis. Then alternatively what we can do is, but if your magnetic structure is commensurate, then we can try to work with this simulated annealing mode and try to see if we can get the information about magnetic structure after removing the constraints from the symmetry analysis. So what I do is, I have to now take this data file which is of paramagnetic phase. So let me, so here are these two data file which is paramagnetic phase, the sample, and this is the data file which is in the magnetically ordered state. As you can see, we have magnetic intensity at low value of 2 theta, means low value of momentum transfer. Now the idea is I make this simulated annealing file. And how I make it? So I add a additional phase. So let me open this file, which is called simulated annealing. And now what I have done is to make this file is, so up to this point, it is the same as your previous nuclear phase, means paramagnetic phase. Only I have put here number of phases 2 because I plan to add now another phase. So I have added this phase, and this phase is Lebel fit. It means it is only profile matching with constant scale factor. To add this phase, we have added this information just before this last line in the PCR file. Now, in this phase, we are not giving any information about the atoms. The idea is to get this integrated intensity of the magnetic reflections. So I have added this phase, and now the important part of this phase I would like to mention. So first of all, we have to write here more equal to 1. What I mean by more equal to 1 is that, so I have written more one. It means I am telling the program that we will have one more additional line. This tells we will have one more additional line in PC. So let's go to the PCR. So when I am writing more equal to 1, I am telling this program that I will have this one additional line, and this is the additional line. Now, in this additional line, what we have is JVI. JVI equal to 11. What it means? It means that we have here J, V, I, and we have 11 code. It tells the program, this code in the PCR file tells the program that it has to generate list of integrated intensity. Integrated also, what are the other important thing in this additional line? Now, this job type, while we add this phase 2, we have to put this job type to 2. And this, what is the meaning of this job type 2? So, the job type 2, JBT, we have written 2. It means it is the PCR file, this phase is profile matching with constant scale factor. With constant scale factor. Okay. Now there is another thing which is like IRF equal to -1 and this IRF equal to -1, which is here. It is just telling it that for the magnetic phase, it has to generate this satellite reflection. Now, let us see the other part of this PCR file. After we have added this phase, so it has only P -1, so no any restriction with respect to the symmetry. And this scale factor, we have to keep it same as was the scale factor for the nuclear phase. We can keep UVW same and this lattice constant A, B, C, alpha, beta, gamma, we should also keep the same. This preferred 1, preferred 2, if you are using here NOR equal to 1, then I should use here 1, 0 and all asymmetry and other thing I can put it 0. Here I have to put this propagation vector which is 0, 0, 0 in our case, and this line is same as in the case of nuclear phase. So this is how we make this PCR file. So what we have done is, I will again repeat it. So this was the contribution till this paramagnetic phase. And we have two more this additional line in the paramagnetic phase. So just before these two lines, I have introduced the parameter associated with this second phase. And now let me close this file and we can see from this edit PCR that whether this file is all right or not. So let me try to open this. So this is simulated annealing. So I will now like to go to the phase number 2 and see. So you can see when I click this phase number 2, due to job type 2, what it comes here is the profile matching. Let me change here the name of phase. It is LINI 0.5, sorry, 0.5 MN 1.5. Now this calculation, this is just commented line. This is calculation means profile matching with the constant scale factor. This is coming because we have given job type equal to 2. Let us go to contribution to the patterns. These are the information about peak shape. We can put it pseudo-void here. Deflection list, which is governed by this IRF parameter. So what we have written here is the satellite reflections are generated automatically from the space group symbol. So this is the condition for the phase number 2. Now, okay. So this is the information about the symmetry and about the calculation of this phase number 2. Now, let me go in the refinement and go to phase number 2. So as you can see here that I don't have any atom and propagation vector I can see it is number of propagation vector is 1 and this vector is 0, 0, 0. Other parameter of the profile like scale I have to keep the same as was the scale for the paramagnetic phase. This ABC coefficient, this ABC lattice parameters and alpha, beta, gamma. Also, I am keeping the same as profile is ever in the paramagnetic phase. This U, V, W, I, G, and other parameters which are related to this full width at half maximum and the shape, there also I have kept them the same. And this parameter, which is G1, G2, which are denoted in the PCR file as asymmetry 1 and asymmetry 2, they are 1 and, sorry, pref 1 and pref 2, they are 1 and 0. So with this, as I can open this file in this PCR, it looks like it is all right as per the format of this full program. Now, what we do, then the idea is, after we have added this additional phase, we try to run this. So I ask run full prof program. And I have to give this data file which is corresponding to this temperature where you have magnetic ordering. So this should be at this temperature where you are seeing fully magnetic peak and you have magnetic ordering. And now you can see it is running. And let's close this. Let us see in this file. So after you run this program by adding this label phase, it will generate a file with the extension int. So this has created a file of the integrated intensities for the magnetic reflections. So let's open this. So now these are the reflections, and accordingly it has calculated this integrated intensities. Now idea is to use this information which we have got it about this integrated intensities in this full prof notation to get the idea about this magnetic structure. So once we have got this, then we have to again make a PCR file. So to get this magnetic structures which are not now limited by this symmetry things. For that, we have to again make a PCR file, and I believe, let's say this is the PCR file. So now what we do? So now we made a PCR file where only we will provide the information about the magnetic phase only. So this is the PCR file now, I have made it. Okay, so in this PCR file also I have put more equal to 1. It means I am putting an additional line. Now in this PCR file, this line is same as you might have seen previously. And now I do not have any restriction from the symmetry point of view. But now I have to put all the position of these atoms. So like in this case, we have 4 nickel atoms in this space group and 12 manganese atoms. I have put this 12 manganese atoms. Now, but you might have questioned that how you get this position of this X, Y, Z, because in the nuclear phase, you have only given the coordinate of one atom. So if you know the coordinate of one atom, what you can do is you can go to this Bilbao crystallographic server. Sorry, y of position in Bilbao. So you go to here. I forgot this space group. So let me just quickly check this space group. So this space group is P4332. I believe it was 120. I do not know, so I would like to choose it from the list. It was somewhere around 120, P4332. Let me check it again. Control F, P43, P4, P4322. Let me see it. P4332. Sorry, this is P4322. We need is P43. So let me just quickly look at 32. P4332. P43. Yes, so it is 212. I click on this 212 number and go with this standard setting. Now, by seeing this coordinate, like you are knowing that this nickel goes to 1 by this 5 by 8, 5, this position. So, at this position, 5 by 8, 5 by 8, 5 by 8, there are 4 other position of this nickel which has been given on this crystallographic site. So from this, you can find out this position of this nickel, another nickel, third nickel, fourth nickel. Similarly, you can repeat this for manganese, which is, I believe, goes on this 12D. So there are 12 coordinates here, and from this list, you can get it. So if you know the coordinate of one, like then you can get this coordinate of others by applying this operation to that position. So with this calculation, you can get all this 12 location of this manganese. 1, 2, 3, 4, 5, 6, 7, 8, 9, 11, 12. So now we have made a file by utilizing the output of our previous step where we have the integrated intensity for the magnetic reflections. Now in this file what I have done is number of atoms. I have to keep as many number of atoms as were the number of magnetic ions in the unit cell. Means all these positions I have to put it. So what we have here is 16 atoms. Like you can see it, 1, 4 nickel and remaining manganese. Now this file, format of this file is slightly different than your powder diffraction file. So this file is more or less in the form of what you will make a file for the analysis of the single crystal data. So this, the information which is there in this file is about this lattice parameter. More or less this format is then related to your single crystal file. This scale factor has to be kept as same as you kept in this last time. Then what is the idea? Now you are writing the moment of each and individual atom like here. But this is a very tedious exercise in this case until you have some idea from some experiment or from some literature that if the moment has some direction or so here what I have done is I have written this moment in terms of this spherical coordinate means r, phi and theta. So what you can do in this case is you can easily put a constraint on the number of on the length of this means magnitude of the moment. So this is the magnitude of the moment on which you can easily put a restriction. And then this phi and theta parameter, either you can restrict them or you can leave them the free. Then you can run this simulated annealing file and then try to see what kind of magnetic structure it gives. So this parameter you have to optimize. I have not optimized so far because I only quickly made this file today to show it to you. So I'm just quickly try to run it. But before I run it, I would like to open it in this studio. Sorry, in the edit PCR. This will give me the confidence whether everything is all right. So you can see it from here, general. This is, let me put this Li and I 0.5, Mn 1.5. And this kind of file for this simulated annealing as well as to create this two-phase with the profile matching already exists on this full Prof website, or you might find this kind of file in the example file of this full Prof program. So you can see it here. I'm just trying to open it and see it how it looks in this editor of this PCR file. So it is writing simulated annealing optimization means integrated intensities. Pattern, neutron constant wavelength. So it do not have now magnetic phase with, now you see in this magnetic phase what we have written is about this calculation. This means how it has to get this information about this magnetic structure. So what we have written here is magnetic phase with magnetic moment in the spherical mode. So this is a little bit convenient in this case because I can easily fix this moment. Then my variable parameters becomes like this theta and phi coordinate. So this part I have deliberately kept it here, and then you can, this intensity is here, reflection list is the integrated intensity. So I am not putting any restriction with respect to symmetry. It's quite free. And so refinement, atoms. Now in this refinement, what you can see the number of atoms 16. So all these 16 atoms are existing here. And I have put this code word M. It means I am telling the program that they are magnetic atoms. And these are this information about this magnetic moment in the spherical coordinate system for all these atoms. This is a little bit long file. So I have kept it like theta phi coordinates. Now other thing is the about constraints. Now we have to keep some constraints to get some meaningful information from this simulated annealing file. What you can do is you can put some constant in this, like you might have some information from somewhere that like moments in these compounds are in the plane. So then accordingly you can put your theta and phi value and then try to proceed it. So what you do is after this, I save it. Then this input file is integrated intensity file. And it will try to run this code. It will try to match this integrated intensity which we have calculated with this model which you are putting it. I have given some constants. I am not sure whether it is correct or not. You can just try this. This is just the idea of telling this is that this is also one of the option which exists by which you can see what kind of magnetic structure you might have. Here there is no restriction from the symmetry point of view. So it is still running. Now, well, it has given some information about this theta phi, and then your idea is to analyze this and what kind of magnetic structure you get it, and then see. And after getting this information, you have to, let's just quickly see. I'm not sure whether it makes some file to see the magnetic structure. File open. So, it is only about, so we have only two studio file, magnetic phase. Not sure. So you can see some information about this moments. I think I have put some little bit wrong constants. So then you can put this constraint, and after you get this fitting, then again what you have to do is you have to make this PCR file again without this integrated intensities, like then after you have done like this, then you can again make a PCR file. Let me see if I have here. I tried to make it today. No, it is with more equal to 1. So let us see if I have. This is paramagnetic phase. Okay. Then what you do is, after you have finished this simulated annealing part, if you don't want to put yourself restricted to this magnetic symmetries, then you can again add a phase, now here without more equal to 1, and then whatsoever information you got from the simulated annealing, accordingly you can put your moment here in this PCR file. Now this is an additional phase, and here there is no restriction from the symmetry point of view, and then you can try to run this and see whether your crystal structure matches, your magnetic intensity matches or not. Let me just see if it, so let me just copy this file in this folder we're working today. Replace this. Okay. So there is some error in this file. I do not know where it. So getting this error solving is little bit tricky part right now. But okay, let us see this file, how it looks. So this is the file as same you will do it with this symmetry analysis. Only I have not put any restriction from the symmetry point of view, and the moments here are in the spherical coordinates. And this is how you can work with this now file and try to see whether this magnetic intensity which are generated, they are compatible with your experimental data. So this is another way how you can proceed it. I hope this clarify your doubt regarding the question which was sent to me. So far now I will change this topic. So I believe now you have understood that how to solve the magnetic structure from this neutron diffraction data. And so far, what we have been working in this series, means in couple of, I think, last 4 or 5 lectures or so, we were trying to calculate or trying to study everything using unpolarized neutrons. So far what we, so let me close this program now. If still you have doubt about this full prof, because now I have only 2 lectures, and today and on this next working day, which is day after tomorrow, and now I will not use the full prof, but still if you have any doubt regarding this part, then either you can raise your hand now or you can send your question later on. I can wait for a minute or so that if you doubt, you can raise now, because now I will change this topic to polarized neutrons. So please write if you have doubt right now. Otherwise, I go ahead. Okay. So far, I think I have not received any doubt. So now let me go to this another part. So far we have been calculating or studying this magnetic cross section using unpolarized neutron. Now, you know this neutron has a spin, and one can in principle do this polarized neutron diffraction. So one can in principle do this experiments using polarized neutrons. Now, so to get this polarized neutron, one must have some technique to produce. The question comes how to produce and analyze polarized neutron beam. Polarization of neutron beam. So we know that each neutron has spin 1/2, and it has, so neutron is spin 1/2 and it has an angular momentum which is plus minus half of h cross. So each neutron has spin vector, and we can define the polarization of the neutron beam. So what is the definition? So how we define? So we define polarization of neutron beam as a expectation value of the spin operator divided by its maximum value. So this is how we define this polarization of this neutron beam. Now the spin has three components. Spin has all three components x, y, z, but in a magnetic field, only component, let's say along the z, is defined. Now, so it is sufficient to consider linear polarization vector in the direction of field for the polarization of the neutron. So suppose Z is applied magnetic field, then how we define this polarization of the beam? We define polarization of the beam as number of parallel and anti-parallel neutrons. So we define this polarization in terms of this neutron which are aligned parallel and anti-parallel to the field. So suppose we are having magnetic field along the z direction, then we can write polarization for the neutron beam as P is equal to n plus minus n minus divide by n plus n minus. Here there are n plus neutrons with spin up, and so these are the neutrons with spin up, and n minus are the number of neutrons with spin down. I am defining up and down with respect to the z axis where I have applied magnetic field. So, and n plus n minus, n plus n minus is equal to n, which is total number of neutron. So now let's take some example to understand that how to get this polarization of the neutron beam. Suppose I have a neutron beam in which total number of neutrons, suppose n is 3000, and out of which n plus each, so 2100 neutrons have spin up and remaining 900 have spin down. Then what is the polarization of the beam? So P as per definition is n plus minus n minus divide by, so this becomes 2100 minus 900 divide by, so this becomes how much? I think 1200. So it means our beam is, this 20 goes, oh sorry, so sorry, this is, sorry, I made a mistake here. So this is 1200 and this is 3000. So this 20 goes, so it is 12 divided by 30. It means 2 divided by 5. All right. So this is how I define this polarization of my beam. So it means my polarization in terms of, this is nothing but 0.4. So polarization of my beam I can say is 40%. Suppose I have 100 neutrons, out of which, let's say suppose total n is 100, n plus is 75 is 25. In this case, my polarization is 75 minus 25 divided by 100. So it means 50 divided by 100. So it means 1 by 2, 0.5. So my polarization of the beam is 50%. So this is how we define this polarization of the beam. Now, what generally we do with this polarized neutron beam, suppose we are interested in the only single quantization axis. Suppose we are doing an experiment in which only a single quantization axis is defined, then generally what we are interested in measuring in the with the polarized neutron beam is, so what we measure in polarized neutron experiment is the polarization P of the beam, which is defined n plus n minus n plus, so this can be written as n plus n minus minus 1 n plus n minus plus 1. So this is what we measure in the experiments, which is called the longitudinal polarization analysis. Now the question comes basically that how you can produce the polarized neutron beam. So let's see now the question comes how we produce this polarized neutron beam. So you know, most common technique of producing polarized neutron beam is utilizing a break reflection from a magnetized monochromator. I will explain how. So how we produce this? We produce this polarized neutron beam by a break reflection from a magnetized monochromator. You know, when we were trying to study this neutron diffraction from a ferromagnet, then you know this nuclear and magnetic scattering interferes, and what I can write is that effective scattering length. So this effective scattering length is B plus. So here this sigma is Pauli spin matrix, and now this structure factor for a ferromagnet for some reciprocal lattice vector, I can write it as exponential. So this tau is some reciprocal lattice vector for which I am writing this expression. Now, this expression I can write it as sum over plus and you know for the ferromagnet case, this nuclear and reciprocal lattice vectors are same. And there is one more term which is called nuclear magnetic interference. B of D R0. So this term is purely nuclear. This term is magnetic, and this is nuclear magnetic interference. Now this last term, which is nuclear magnetic interference, when you are dealing with this unpolarized neutron beam, this term becomes zero. Now one can use this technique or this ferromagnets for a special case, for suppose for some material, let me erase this. suppose B of this nuclear scattering length and this magnetic scattering length suppose becomes 0, equal. In those cases, as this sigma can be either +1 or -1, so for one of these cases, you will reach that you have this reflected beam, but other case, the intensity is 0. This is how you can produce this polarized neutron beam. And in the next lecture now, we will briefly understand how this polarized neutron beam can be used to get this information about this sample. So in a typical experiment, when we are using this polarized neutron beam, what we do is we go to some back reflection, back peak, and try to measure the intensity of this peak in the flipper off and flipper on condition. So I will just quickly write it what we measure. So what we measure is this flipping ratio, which is to flipper off, flipper on, the ratio of intensity. And this has important consequences. Suppose you are doing an experiment with a ferromagnet and your idea is to determine this magnetic moment in a ferromagnet, and suppose moment value is quite small, something like suppose Fm by Fn is. So when you do this experiment using unpolarized neutron beam, your enhancement in the intensity goes as, and this factor becomes very small if Fm is, because this is the square of this part. So this becomes like 0.01. However, when you are measuring this flipping ratio, you can see this. I can write this R as 1 plus 4 times of Fm by Fn. So this quantity I can easily measure it. So it means by utilizing this polarized neutron, I can easily get the information of the very small magnetic moment if it is present in my sample. We will understand this part in this upcoming lecture, which is on Friday at the same time, 3 o'clock. Now, if you have a question regarding full prof part, you can please ask.
Regarding the magnetic space. P1. Another program as in JNA 2006, I found it uses another magnetic space group like PNMA 0G0000.
Okay. So this doubt nowadays in the full prof, there is a additional feature. So you can give this magnetic space group. So this magnetic space group feature have recently been added in this full prof. So you can do this refinement by using this magnetic space group. But this one has to see the case by case that what kind of magnetic space group is present. The formalism which I have given about this propagation vector, it is more general formalism and it can be applied to both commensurate and non-commensurate structures. This magnetic space group, which are called Shubinko space group, they are limited to these commensurate structures. So in this lecture, I have tried to give you the flavor regarding this propagation vector. And this is most general formalism which can be used in any case. I'm sorry, I will try to give them to by today evening. So hopefully by tomorrow it should be loaded in the server, or maybe in a half an hour or so.